All right, so still have people joining, but we do want to get started so that Dr. Abdullah has the full time to give his webinar. So just really quick, good afternoon, everybody. My name is Sarah Grasty. I'm the Outreach Manager for COMIT. Thank you so much for joining us today for our August webinar. Hopefully we'll continue to see you all as we continue this monthly webinar series, which focuses on a large range of topics related to COMIT's research goals, such as technological advances related to seafloor mapping, operational applications of hydrography, safe navigation, and beyond. So I hope that you will continue to stay engaged with us via our webpage, newsletters, and social media, so you can, stay up to date with events just like this one. I will drop those links in the chat in just a second. Next month for our webinar, we'll be joined by Dr. Meg Palmston from USGS, and in October, we'll be hosting Dr. Brandon Jones from NSF, talking about diversity and equity in the geosciences. So now I'm going to hand over the mic to our Center's Director, Dr. Stephen Morawski, to introduce our distinguished speaker for today, Dr. Qassim Abdullah. After Dr. Abdullah's presentation, we will have time for questions, which you can use either the chat or raise your hand feature. And then Dr. Abdullah has agreed generously to stay behind after that initial question period to just meet specifically with students. So please try to take advantage of that if you have the time. So with that, Steve.
Yes, thanks, Sarah, and thanks for setting this up, and welcome to everybody who's online. I see we've got a really great turnout for the seminar today. So our seminar speaker is Dr. Qassim Abdullah. He's a very accomplished scientist, has over 40 years of combined experience in industrial research and development and academics. His expertise is in analytical photogrammetry, digital remote sensing, and civil and surveying engineering. Currently, he's the vice president and chief scientist at Woolpert, which is a very large international company doing mapping related work. Additionally, he's a adjunct professor at the University of Maryland, Baltimore County, and serves as an adjunct professor at Penn State as well. I know that classes have started there. Dr. Abdullah is also gives generously of his time. He's a member of the NOAA Hydrographic Services Review Panel, HSRP, which is having a meeting next week, and certainly, people who are interested in all this can sign up to do that. He's also on the National Academy's Transportation Research Board, standing committees on new users of shared aerospace, and the Standing Committee on Geospatial Data Acquisition Technologies. Dr. Abdullah obtained his doctorate in photogrammetry from the University of Washington at Seattle. Just in terms of some of his awards, Dr. Abdullah is a fellow with the American Society for Photogrammetry and Remote Sensing, was the creator and principal author of the new ASPRS positional accuracy standard for digital geospatial data, and he received the organization's Lifetime Achievement Award in 2019. He also has numerous other awards that he's been granted. He's a professional certified photogrammetrist and a licensed professional surveyor in Florida, Oregon, Virginia, and South Carolina, so a lot of licenses to keep up. And he's a certified thermographer as well. So with all of that resume, I would ask Dr. Abdullah to give his presentation on advancements in geospatial mapping, sensor technologies, and procedures for inland and coastal mapping. And thank you so much for giving the webinar today.
Thank you very much, Steve, for your kind introduction. Good morning, everyone. Good afternoon, everyone, wherever you are. I would like Steve mentioned, I will try to brief you on where we are as a geospatial industry and in terms of capability, technology, procedure, data, and so on. And I will focus at the end on the coastal mapping and hydro survey technology and status and example. So I would try to stick to this agenda, current status of digital imaging technology, and so as for Lidar, surveying technology, current experience with multi-beam sonar and unmanned platform, and new and future advancement and the coastal mapping technology. So I just a brief introduction to Woolpert. We are what we call AEG, Architectural Engineering and Geospatial, and we have about 1,100 people globally, 40 plus offices worldwide, and we are the oldest company in the United States engineering surveying, established in 1911. And that's our market. It goes all over the spectrum: aviation, education, parks, transportation, maritime, and so on. And here's our asset. We are proud to claim like we have almost every technology the geospatial industry involved with or needs. And so the highlight of this talk, it is just to convey to you the exciting time we are living in. I mean, definitely we are in a stage of technology. It cannot be better, although I know it will be better. That's what we said 5 years ago and 10 years ago, and we keep proving ourselves wrong. Those are technology and manufacturer. They keep surprise us with this advancement. So we are, as geospatial industry, we really reach new heights in data acquisition and mapping products capability. I will try to demonstrate that. And such a revolution of technology, really fueled by amazing technological advances from sensor manufacturer. And I would say thank you, because those are tirelessly continue surprises with improvement and advancement in the technology. Every 6 months become like your smartphone. And the federal program, that's what the driving force, because manufacturer and sensor by itself, we will reach a point where if nobody buy the products, it's not going to lead to any advancement. But the federal program that fuel this cycle of development. So example on that, the USGS 3D program, keeping everybody with the aerial Lidar nationwide, definitely. NOAA Coastal Program highlighted, I just want to highlight the National Strategy for Ocean Mapping, exploring and characterizing the United States Exclusive Economic Zone. That's last year was being approved, and we're looking forward for that, for the start the implementation plan. And Alaska Coastal Mapping Strategy, that helped a lot the industry in pushing the limit, definitely in the technology. And the Corps of Engineering, the USASC, and their federal partners through the JARTEX program, the National Coastal Mapping Program, and CMP, and those are the main figures, definitely, between these federal agencies, which pushing us hard, expecting us more from us, and in turn, we push the technology to make it more productive and more efficient. So if I look at the digital imaging, what you see here is some of the digital imagery from high altitude, but you see the quality of digital camera now. And the reason, because the advancement continue on the digital camera, so you have a great sensor in the market, the workhorse, example, Hexagon ADS 100, 20,000 pixel wide, Vexel Ultracam Condor, almost 38,000, and Hexagon DMC3, which is almost 26,000. That's a huge capability in the coverage, in the swath with on the ground, beside the quality. As the colors, we never seen in film color photos like this, because the dynamic range of the digital camera, you talk about 14 bits and 11 bits of data, it gives you amazing information whether shadow or not. And now we added the drones capability. Definitely the drones advance in the last 5 years tremendously. I mean, we're getting awesome metric data from consumer grade camera on this drone. And if I This is one example of this consumer-grade camera, 3D model, texture model, colorized with the RGB. It's just beautiful. I mean, like if you asked me 5 years ago, I would never believe such consumer-grade camera on the drones can be used to create this photogrammetric model. It's very accurate, very precise and detailed. And as of ortho, those are sub-inch resolution standards with the drone. We could not afford it with our metric camera before, unless we put it on helicopter, which we did for DOT to get 1-inch resolution. But the problem with that get very expensive. While with the drones, it give you 1 to 1.5 centimeter on regular basis, and you see the detail, cracks on the pavement. You can read license plates if you have a good angle on it on the ground. So LiDAR, I'm gonna brief you about LiDAR, but I know there is some of our students, they come in here to learn, and I would like just for people not familiar with the LiDAR, just to give background, because I don't want to talk to somebody about something they don't imagine what it is, this amazing technology. So I will go quickly a few slides just to overview what is LiDAR. LiDAR is an acronym for light detection and ranging, and it's a simple physics. Laser light sent in the space, and when it hits solid object, it returns. That could be a bird, a flying bird, could be power line, it could be tree, it could be the ground, any solid. Some of these photon, the energy goes back to the sensor and we receive it, but there is very accurate time in clocking in and out, because we know the speed of light, and I think I have a slide, I will go through it before I jump into that. So the facts about LiDAR: designed to measure a 3-dimensional coordinate point on the ground, active laser system, it generates its own energy. So the nice thing, it works day and night, not like our cameras, only during the day. Most LiDAR systems operate in the near infrared or the green region of the electromagnetic spectrum. The advantage of the green for our maritime industry, the green laser can used for shallow bathing because it penetrates the water column. And what you see here, that's just to show you in the graphic the different spectrum region of the electromagnetic spectrum. So the LiDAR pulse, it travels as a flashlight, is a light actually, and when it is emitted, the precise timing is recorded. Time 0, the reflection of the pulse is detected, and the precise time is recorded at time 1. And using the constant speed of light, the delay T1 minus T0 can be converted into a slant rate distance. You divide it on 2 because the rounded trip, you get the range. And we put on the sensor IMU and GPS, so the range plus orientation and position, we convert that where it hit the tree into XYZ, and that's the point clouds. Let me just show you how it is. The laser emit to an oscillating mirror, very quick, because this is not a profiler. It covers swath width. We want to cover as much on the ground to reduce the amount of flying in the air. So that oscillating mirror separate the pulses left and right of the aircraft, and it gives us wide swath, depends on the altitude. It could be 2 kilometers, 3 kilometers, and so on. And this would really show it. This simple graphic shows you that's exactly how the LiDAR is. There is some of them circular, by the way, but that's the sinusoidal left or right scanning. So what does LiDAR measure? Measuring ground, roads and other surface feature, vertical structure of vegetation, structure, submerged topography with the pathy capability. And that's what you look at the point clouds. If you collect them, well, that's what you see really. Every dot of those we call it point cloud, is X and Y and Z is flying in space. That's what we determine from the range and the orientation of the sensor. Typical LiDAR product, the digital surface model. That's the majority of our product is digital surface model, point cloud to represent the terrain. And then we have another product, it looks like an image, it's not really an image, as we produce as a raster. And that's what we call intensity image, but it can be used like the image because that has the same geometry of the point clouds, the accuracy, and what you see on the image on the right. This is taken from a Geiger mode. I'll talk about it a little soon. Intensity image, density 30 or 40 points per square meter, and that's what you see, the taxiway and the runway details. You can definitely use it for mapping linear feature and others like that. And the other product is a full waveform digitization, and that's very effective in the forest area. Forester uses it a lot because it can see under like new growth and their old growth, and using the signal processing, utilizing the return of the signal of, if you see on the left, because the pulse we're talking about is not 1 point, is a flux of photons, around 500 to 1,000 photons. So when it hits a branch or a tip of a leaf, some of these photons return back to the sensor, and some of it continue to the next hard object. And that's all our radar has a multi-return capability. It sends one pulse, but it receives segmented pulses, and it records the time, which convert to range, different ranges on where it hit or how far it reached. A platform for LiDAR, a helicopter, fixed wing, mobile, on the ground we drive it, unmanned, hold it on, carry it on your back now for interior scan. It is going everywhere, definitely. So the state of LiDAR technology, no less than the digital imagery. Actually, it is more advancing much more now because the demand on LiDAR is high. So the manufacturer definitely filling the market with great innovation every day. And the LiDAR market is very strong with high demand for higher density and better quality. LiDAR become an integral part of project planning, design, and construction. No matter what sector you are, whether transportation, maritime, or engineering and construction, LiDAR going everywhere, definitely. The state of LiDAR topo system, and topo, what I mean, that's for inland topographic LiDAR. I just want you to differentiate it from bathy LiDAR. And topographic area LiDAR, massive capability in a 3D mapping of terrain and infrastructure. And what you see, just example of this point cloud, the density, whether power line you want to model, whether building, bridges, and the stadium you see as a very capable technology to serve all that. So LiDAR give us really everything we need to support the national 3D program. This is some views from our latest project with Alaska, the Big Island, which is very challenging. If you ever familiar or flew or try to fly aerial in Alaska, it is very challenging environment between the terrain, the thick vegetation, the weather is hard to get. While this one, we utilize a single photon technology, which I will define it later for you. We were able to map it efficiently, precisely, and accurately. And LiDAR is a backbone photographic and infrastructure mapping. What you see here, you can model bridges, roads, building, and so on. And that's you talking about accuracy of centimeters, by the way. And we fly it from 10,000 or more altitude above ground. And among those innovation by the manufacturer. Here's Teledyne Optic. They have the Galaxy Prime, and by now probably they have even something better. And Regal, they have a suite of a product. Among them is the Regal VQ780 and so on. And Hexagon and Leica, which with their latest terrain mapper as a linear mode LiDAR, and the SPL, the single photon LiDAR, SPL 100. If we look at the mobile mapping system, what is, it's again, the market has at least 6, 7 great mobile mapping system. And those are, you put it on a truck or a van, they collect data, very dense. You talk about 2,000 to 6,000 points per square meter. So imagine 3 feet by 3 feet. It has 6,000 formation X and Y and Z. It traces the scene. It give you to the micro level detail of the terrain or the feature. And the accuracy, you can get 1.8 centimeter vertical accuracy as a 1 sigma root mean square, or even better if you need to. And that's the product from it. We can generate contour, we can generate a break line for geospatial modeling, or you can use it for asset management. The mobile mapping is a great road, actually is the only efficient road asset inventory and management, because it's done by hand with somebody driving a truck or riding on a pad. While this one, it gives you an image like you see in the middle of the screen, and XYZ, accurate XYZ. So you can document pavement management, material distress, routing, and so on, traffic signal, sidewalk, all the things you need for roads inventory and engineering. And now in the last few years, the UAS-based LiDAR came very strong. There is we started with one brand, and now we have at least 7 or 8 brands of those LiDAR. Lightweight, miniaturized system. You can put it on the quadcopter that you see on the left here. And you can get point density from 600 to 900 on average, but some of them give you much higher density accuracy. You can reach 2 centimeter vertical accuracy, and altitude you can fly 70 to 300 feet, which is within the regulation of the FAA. The state of terrestrial LiDAR is the one you put on a tripod, and that's a great tool for surveyors to survey indoor or outdoor building, industrial complex, and this came in a good time for the digital twin requirement for that kind of model, for example. And here you just see example of this 3D model. The one on the right is not an image. This is really looks like an oblique image, but it is a 3D model texture by the color from the image as a great way to model building inside and out. And now the bathymetric LiDAR. LiDAR enables us to map the seafloor and coastal areas with unprecedented accuracy and precision and detail. And what you see here really on the screen, that's a sample of a product from this bathy LiDAR. And for example, one of our latest experience with difficult to obtain data is the North Mariana, Central North Marianas Island and Northern Hawaii Island. Those are, although they are small, but they are very remote, which make it impossible for some aircraft to reach. But we were able with this kind of technology to reach it, and distance between them far. So it's a small area scattered, but with the performance of this scanner, we were able to map it with the highest precision, definitely. This is 2 examples for the Pagan Island and the Saipan Island. and you see the detail. This is shallow bathy. This is topo bathy with a green laser LiDAR, where you can get, you see the coastline, the shallow, and the inland, for example, with this kind of detail. Is amazing technology, definitely. And again, in the market by this great system with Regal VQ880G and the Seasmil, many of you familiar with it from Teledyne Optic. And we definitely investing a lot in this technology just to strengthen that capability for our client. We have our asset, and I'm sure it's more added now, 4 popular tide gauges, profiler, 11 pressure tide gauges, 1 multi-beam echo sounder, 2 turbidity. Beside the deep deep bathy, we have 2 or 3 of them, for example, the Leica one. And the latest new aerial system when it comes to LiDAR and imagery really is the combining LiDAR and cameras, oblique camera, in the same sensor. And what you see here, this is a product of it. If you zoom on, that's what we call oblique imagery. You get all the facades of the building and the roof to model a 3D. And that's the one on the right. That's from LiDAR, the same flight, same sensor, has camera and LiDAR. And that's an example of the Leica City Mapper 2. So what is next for Topo LiDAR? Like I said, I showed you, I told you is a great technology, but is anything left? And I say yes, because in the last few years, if you're following the technology, you start hearing about Geiger mode, single photon, flash LiDAR, and that's really the latest and the greatest things we start using, and we keeping an eye on it for further development. So what is about this technology? What is different from the LiDAR we are using? Is not much, because it's the same laser physics, it's the same all the stuff, like the figure I showed you. A laser pulse, send, and it comes back. With the current, what we call linear mode LiDAR, the one I showed you earlier, we send a pulse and we receive it back as a pulse. Maybe when it breaks, we receive it 3 or 4 sub-pulses. That's it. But the manufacturer was very creative in the last few years by this design about thinking how you harvest this energy. You have a limited budget for the energy on the aircraft to generate these laser pulses. And we've been using, we send one, we receive one, send one, receive one. So they came up with what we call an architecture really similar as a laser-based digital camera, I will call it. And if you look at the image on the left, is really they came up with the optics. They put it in front of the laser pulse to segment it into sub-pulses. And that's the whole thing, the excitement came about this technology. So when I don't send a pulse and receive a pulse, I'm gonna send a pulse and I receive maybe 1,000 of sub-pulses. Each of the return one, it will be XYZ point cloud. So it'll be 1,000 of point cloud. So you see the graphic on the right, really the linear LiDAR is a concept of 1-to-1, while the single photon and Geiger mode is 1-to-many. So you see here, we send the pulse, it gets split into multiple sub-pulses on the tree here, what you see, and we have segmented anodes to receive them. Every single sub-pulse, it has its own channel to receive it, like you see on the left now, and that's how we multiply exaggerate or amplify the energy. For example, instead of receiving one pulse or resulting in one XYZ on the ground, I get hundreds or thousands of them from sending one pulse. And this is just one example of the Geiger mode avalanche photodiode by lightwave, Princeton Lightwave. They don't exist the way they are now. They've been bought by Ford, I think, lately. But that's a typical Geiger mode camera. This there is 32 by 32 pixel and 128 by 32, scalable to a larger format. So advantage of single photon and Geiger mode is ability to fly higher and faster. Altitude of 9,000 meters is possible. Provide extremely dense surface model, average of 35 points per square meter. Although we can do it with the linear mode now, but it gets very expensive. While this one regularly you fly it very high and you get 35 points per square meter. Better penetration in trees, vegetation, fog, and clouds. And the penetration in trees, just because the density, you have a better chance to go through the void and gaps in the foliage or in the canopy. Each range measurement requires only one detected photon as opposed to hundreds of thousands or thousand in the conventional LiDAR. Like I said, the flux of energy in the linear mode, 500 to 50 to 1,000 photon, while this kind of hardware, you really need theoretically one photon to trigger it. That's the advantage. And significantly less mass, volume, and a prime power. Our contribution, which I'm proud of and I was in the middle of it, is Woolpert developed the first high altitude single photon LiDAR for the US government. And they fly in it now. It flies at 25,000 above the ground feet altitude, that's new because our standard at the time, 3-4 years ago, our standard altitude around 7,000-8,000 of the LiDAR. This is all the way to 50,000, and it provides point to cloud density of 8 to 12 points per square meter, and you can get from a single pass, and you can get better definitely. Here is just some example of the single photon LiDAR sample. This is just to give you as a frame of reference of density, 25 points per square meter. Here is we flew the single photon at the time to benchmark it on Mecklenburg County, North Carolina pilot. We work with Sigma Space at the time, which acquired by Hexagon now. And that's a sample you see, it is 15 points per square meter. And you see the power distribution net, you see the power line is so clear with LiDAR. That's all three-dimensional XYZ. Here is another example from single photon LiDAR, average around 30, I would say, point per square. That's over Connecticut. When we evaluated the technology, they hired us, UAGS contractors to evaluate the single photon and Geiger mode. And we flew a county size 500 square mile worth of area in Connecticut. And that's what you see, part of the sample of the area. You see the building nicely formed because that single photon, it's scanned at 9 degrees, so it can give you oblique LiDAR, which is kind of new, which is useful for a 3D of the building where you get the facade. So now I just want to give you some example of our current involvement as industry with the uncrewed bathysphere survey vessels. This is, we team up with IXBlue on a project using the DRIX. And the DRIX is an 8mm unmanned surface vehicle. And it can carry various onboard sensor capability, Lidar, radar, whatever, on multi-beam. It directs, analyzes environment, avoid obstacle, and carries out its mission autonomously, which is kind of nice. It has a human eyes on top, represented by technology, different technology, so it can manage itself. And here is the project is for Saint Pierre and Miquelon Island is a French territory close to Canada, if you're not familiar with it. And you see on the left, you see the tracks that the Drix took, and on the right, sample of the ocean bottom. Is amazing detail. This is amazing detail without any human interference on boat or something by unmanned. This is another example of the data and the boat on the left, or the fog, and there. And on the multi-beam bathymetric survey, our latest experience, we conducted multi-beam bathymetric survey in the vicinity of Fort Lauderdale in Florida to support testing conducted by Naval Oceanographic Office, the NAVO, using the SEASMIL and the PILS bathymetric LiDAR sensor. And the purpose of the multi-beam data was to provide a comparison data set for evaluating the LiDAR accuracy and target detection capability. So there was some buried or sunken or submerged target like pipeline, barge, and IRMA center. And here is just example of the data for the barge and barge detection here. And here is for IRMA center, looks like some targets in the floor, the ocean floor. And here is the pipeline and how you can detect it definitely very clearly. And another project is we contracted by the USGS to provide and process topographic bathymetric LiDAR data and 4-band digital imagery for 2 rivers in Colorado. We conducted a simultaneous collect of topographic LiDAR and bathymetric LiDAR using its Leica Caropetra 4X sensor in areas of the river that were too deep to wade. Woolpert utilized sonar to measure bathymetric points. And thus we help the USGS to really to collect ground truth, because where they can drive or walk, we can collect data for verifying the accuracy. So use single beam sonar was collected from a small portable unmanned survey remotely operated from shore. And we put on it CE hydro system echo with 200 kilohertz survey grade echo sounder was used. And this, what you see here, that's really the boat. That's the product of our maritime research lab, which I'm proud of, where they put the echo, the technology, and the unmanned to make that unmanned vehicle, so we can send it anywhere we want while we're watching it from the shoreline. So what is next for Bathy LiDAR? By all means, like our clients wants, increase efficiency and productivity. It's like Topo LiDAR is like imagery. People want more point, denser point, more accurate with less cost. And we definitely working on that with our technology partners to make it happen. So Woolpert in the last couple of years formed the Woolpert Maritime Research Lab to focus on these urgent requirement for us and our client. Through contract, supporting that research lab is a contract with our government and industry client. And we are working on increase efficiency and productivity, introduce off-the-shelf technology to model surface topography, improve geometry, increase the spatial resolution, and the use of the more or less real-time total propagated uncertainty, the TPU, which some of you might heard about it, but now here we're talking about real-time, applying it to real-time, and with a little bit different too. So why we mention or we having the TPU one of our goals to work on in the lab? A very simple answer when somebody say why we do accuracy analysis, why we verify accuracy. Because all our surveying and mapping sensor and all our measurements, physically, when you do measurement, there is always errors. No matter if you use the most accurate laser to measure a length, if I give you the laser and repeat it, the laser gonna give you different answer each time you measure it. If I give you a steel tape, if you are a surveyor and give you the most accurate and precise steel tape and ask you to measure the length of your desk, and you repeat it 100 times, and believe it or not, you're gonna find yourself every single time you get that fraction, 1,000th of difference between them. And that's acceptable because our human knowledge, we can, the exact value is elusive to us. We can't realize that. By measurement and observation, we get close to it. And that's where the whole concept of statistic and accuracy. So the TPU is part of that measure. It gives you good measure to make sure your data is okay, whether it is during flying an operation or afterwards, for example. So bathymetric Lidar, there is sources of uncertainty, trajectory, XYZ, omega C, roll and pitch and head from IMU, board side of the IMU, sensor measurement, for example, the laser ranging, water characteristic and ranging, and just to mention a few, there is a lot of source of error. So the total propagated uncertainty give you a good way to give and to get an idea and provide an idea to the user about the how confident you are in this point cloud, for example. So, and it depends how much is acceptable to you and to your client. Are you trying to meet surveying and mapping grade or tighter specification or standard, for example? So that's all need to be in the discussion, definitely, about the data. So the TPU, what we are doing different, two things really, the main two things. We achieving it by real time, so we give the operator the ability while they're flying and collecting, they can look at these TPU figures on a screen, a graphical, spatially distributed, to tell them whether the data has something wrong and they need to stop or recollect, for example. And we are using nested approach, MATLAB, C++, CPU, GPU optimizations, and CUDA and C++. So we're experimenting a lot, and we achieving it now in the lab. We're gonna deploy it on the field. And if you're familiar with the TPU, the traditional one, it models 17 parameters. You know, the error I mentioned, the source of error from trajectory down to the water and water column. And that's people talking about it for the last 10 years, no brainer about it. But what we introduce now with the introduction of better sensors, bathy sensor like the Geiger mode, we get in better density. It enables us to get the sea surface topography, which was missing in modeling the TPU. So we added the 18th parameter there to complete. And if you think about it, before we just deal with the sea surface as a flat, but there is no such thing, right? There is always a turbulence, there's wind and waves, and without modeling it, your refraction or the modeling of the light ray when it goes in the water will be effective negatively without knowing what the water surface topography modeling it. And here just to show you a little bit about that. Geolocation error and uncertainty are amplified when a flat surface, and you can see the difference between the two graphs. Definitely, it exaggerates the problem, for example. So, in a nutshell, you don't get the precise topography of the seafloor, as if you're not correcting for what the water surface or topography or the shape of it. And the nice thing about developing that concept of TPU with its mature model with the 18 parameter is it enables us to evaluate which technology is better and good. For example, is it Geiger mode? Is it linear mode, for example? And here, if you look at the kind of toward the lower middle of the screen, that's what the operator on the plane, they will see. This is a TPU graphic. It shows you colorized according to the problem it has. The middle band is where is brown, reddish. That's no good. Maybe exceeded the threshold. The green on the side is better, and that's where it attracts his attention to figure out the problem or stop, to not waste too much time on it and restart your survey, for example. That's Steve, that's all I have here, and we have about 10 to 13 minutes for question and answer. If you want to open it, I'll be glad to answer.
Yes, thank you so much, Qassim. Excellent seminar, and a lot of information there about capabilities and how they work. We have a number of questions people have already put in the chat, which I'll read out to you. And also, if you want to ask a question, if you go up to the top of your of the bar, you can just get that little smiley face with the hand and hit that, and it'll put a hand up for anybody who wants to ask a question. So I'll read out a couple of the questions that we have, and please feel free to ask any other questions you might have. Mike Schmidt asked the question, what are the processing pros and cons of the Geiger model mode and their relative acquisition cost differences?
You know, once you build a system, definitely the Geiger mode is going to give you much denser point. I mean, that means larger volume of data you have to go through. But with the advances in the hardware and the processor speed and the parallelization and the cloud processing or storage size, really this has become very, I mean, 10 years ago will be a problem. Now I'm not worried about that. And what's the second part? Sorry, Steve, about the...
It was about the cost acquisition relative to the standard mode.
The acquisition-wise, probably will be more productive, will be, and the operation in the field will be probably definitely, and I didn't highlight, I'm gonna take you back if you don't mind, and I'm gonna share my screen to show you that graph, which I didn't highlight, because the Geiger mode, the one at least we are building, you fly it much higher with a bigger swath width. And I'm gonna take you back to my, here you go. So if you see to this graphic, look at the cone. the problem with the current bathymetric survey, you really have to fly very low. I mean, you talk about hundreds of feet, few hundreds, 500. You can't fly them much higher. While with a technology like this, we can fly it at 10,000 feet or maybe higher, for example. So you see how, so cost and the acquisition probably will be much more efficient than what we're doing now with the linear mode bathy. Cost of building probably is a new system, probably will cost more, but once it becomes industry standard, it will go down to a regular price.
Great. Yeah, actually, I wouldn't mind following up a little later on the beam spread. So Clark Alexander asked a question. Says, unfortunately, bathy LiDAR systems are of little use in turbid waters, light penetration around 1 to 2 Secchi depths. Are you working to increase the usable penetration depths with better processing? That is,
yes, yeah, absolutely. I think our maritime lab working on that, and we're seeing an opportunity with the Geiger mode definitely to function better just because the density better in the turbid water. Yes.
Yeah. Dave Narr, do you have a question?
Yes. Thank you for your lecture. I really enjoyed that. I had a couple questions about the Geiger mode in the sense of backscatter intensity. Does it also collect those data, or is it lost when you go to the Geiger mode?
Geiger mode, at least the one I tested, unfortunately, it doesn't really have the capability for intensity. Single photon, you can, but Geiger mode is a binary system, either closed, shut, or open, and that it doesn't allow you to receive the photons like the single photon, for example. That's in general as a Geiger mode.
Okay, my next question is, this new Geiger model sounds like it could be used with aircraft flights of opportunity. If you have commercial flights going from one place to another, you could attach such a system to a commercial flight. Is that a possibility or a thought?
Absolutely. I think, I mean, that's the same discussion when we are at HSRP, and ideas about why don't we put these sonars on a cruise, for example, right. Boats, and they go all over the so it is possible, and make it possible for Geiger mode, just because you can fly the one we working on. You can fly it maybe 10, 12,000 feet altitude, but eventually I'm sure we can push it like we did with the Topo one, 26,000, for example, altitude, the one Hertz built, for example. So it is possible to put it on an airplane, yeah.
And one last quick question for the Colorado River study. I noticed you were using a single beam sonar. I was curious why not use a multi-beam sonar to overlap with the LiDAR work on those rivers.
Well, because that's a good question, but really the purpose of this single photon, the single sonar, we just want to collect kind of profile, because they usually did it with surveying, boot on the ground. And when they can't wade through the water, that's why the sonar being brought into the picture. That just to add in that, yeah.
Okay, thank you.
Sure.
Yep. Sarah, do you have a question?
Yeah, thank you for the talk. That was really interesting. I'm a fish person by trade, so this was much different for me. But Dr. Nar's question actually just made another question pop into my head as far as issues of national security. I'd assume that with the level of detail you get from these systems, if you did put it on commercial flights, that could become an issue. I guess I'm just curious, especially using them in coastal environments, like what issues have you run into, and how do you deal with that?
Sarah, do you mean like privacy, maybe?
Well, just, I mean, if you're getting that level of detail, especially with the photography of these things, there are naval bases and such like that, you know, if you were to be able to fly over somewhere with this technology, you know, I was curious if your company has ever had to deal with significant issues like that.
No, absolutely, because there is always areas in the nation where you cannot fly over it, right? There is various area, so we have to get approval ahead of time, and the charts from the FAA, they show you where you cannot fly, for example, or maybe certain altitude. Everywhere else, we are allowed to collect this kind of resolution, because this discussion, Sarah, came very strong now with the drones, because our high altitude, we collect maybe 3-inch from manned aircraft on regular basis as a best resolution. But with the drones now, we collect 1 centimeter, and people, I mean, you're gonna look at somebody backyard and pool. So it brought the privacy issues, and this is never resolved. There is no FAA regulation say you cannot do it, neither national. But for national security, there is some area nobody allowed to fly over it, definitely.
Just to follow up on that, this is not so far-fetched as you might think. NOAA currently has a program where they attach sensors to commercial airlines to do vertical profiling of temperature and humidity and all that, and it kind of replaced the weather balloons they used to fly. You know that there's so many takeoff and landings that you get much better vertical profiles, from those kinds of sensors. So it's not beyond the realm of possibility to add sensors to those packages. Very interesting.
And that, thanks, Steve, for mentioning it. That goes across all technology we're dealing with, because the same I'm involved, like you mentioned, with the TRB a lot, and now with this autonomous vehicle, for example, they need very accurate, updated map in real time. So a lot of idea. Why don't we put these Lidar scanner on taxis, for example, and UPS and FedEx, they go everywhere, and they roam through the same street few times a day. That's nothing better than updating in real time like this. So that's all valid, definitely, whether on cruise boats or on taxis or UPS or jetliner, definitely, yeah. And I think it will be, eventually it will be there, yeah.
So I have a different question for you, Qassim, and that is, you mentioned the notion of trying to understand the total accuracy of measurements, and I wonder if you've been involved in any projects where you've actually looked at comparing the precision of estimates between something like a multi-beam ship-based sensor versus a topography Lidar in either mode over the same bottom to basically see what the relative precision of the instrumentation actually is.
And I'm not directly involved, Steve, but yeah, this has been done. And even with Woolpert, because you saw one of the multi-beam we did for the USGS, for the other project, really to verify the accuracy of the bathy, the deep bathy, for example. And I was involved in the comparison, but maybe it is going on. But yeah, that's the only way. That's a problem with the topo. We don't have problem because we can have ground control and verify it to the centimeter level. With the bathy, there's still a lot of work need to be done. We need the calibration centers. I hope, like between NOAA and the Jabal Techs, we establish some targets. I think they're working on it. Probably I wasn't involved in seeing result from it. You need the calibration centers where people can fly their bathy or multi-beam, and we can verify exactly what is the accuracy of the precision of each technology.
Frank Mueller-Carter, do you want to ask your question as well?
Well, thank you. Yeah, thank you for a great presentation. I had the same question as Steve. Many people are using visible satellite images or now from drones or things like surface motion. And I wonder what when these techniques allow you to map over very large areas, even globally, as opposed to with the LiDAR. So what's the differences in accuracies that you find between the visible mapping using spectral data and LiDAR data? And
we're not talking now about Bathy, right? We're talking about, no, that's I'm very clear about. You know, with the drones, our latest project and verified accuracy with independent checkpoint, vertically you can get 1/10 of a foot from drones, believe it or not. And so as horizontally from aerial manned aircraft, our regular bread and butter, when we fly a 3-inch, which is like 7.5 centimeter GSD, we can reach to root mean square error in X and Y down to 1 pixel, believe it or not. But we usually promise 2 pixel, like 15 centimeter accuracy. So if your GSD 7.5 centimeter, you expect the horizontal accuracy around 15 centimeter. It could be down to 7.5 centimeter. I'm not involved in satellite a lot. I mean, definitely we are getting resolution GSD of 1 foot now, but I never involved in evaluating what is the best thing you can squeeze out of it, but it cannot be like the aerial imaging, definitely.
Yeah, no, the numbers you cite are impressive.
Yeah. Well, I'd like to see if we can, we've hit our 1 hour limit. I'd like to keep on schedule. I know I've got a lot of other questions, but I'll try to maybe send you an email or something like that.
Sure, absolutely.
Please, number one, if you're a student and want to ask Qassim a few questions or interact with him, please stay on. If not, I'd like to thank Qassim and give him a big round of applause. We can do that virtually, if I can get that right, and we can do this, you know, in sound space. Thanks so much.
Thank you. Thank you.
Great seminar, much appreciated. I know we all learned a lot.
Thank you.
So thank you all, and please join us next month for another exciting seminar. So thank you all.
I will wait to see if there's any question.
Yeah. Okay.
Let's see. We've got Matt, who isn't technically a student, but always has good questions.
Yeah.
Okay. I always not had the question
either. Yeah. No, thanks for the talk. Always enjoy. I've been attending the HSRPs for the last couple of years since they've been more accessible virtual, and always appreciate your comments there. And
thank you.
This seminar was no exception. Yeah, thanks for doing this.
Sure.
Now, I guess maybe I have a couple of students here. I'll throw this out kind of on their behalf. We talked a lot about technology today. My route to academia was via like a decade and a half in the private sector. But I imagine some of our students are maybe looking to do the reverse when they graduate. So if you have any insight for them on what sort of skills or modes of thinking or anything else that is in particularly high demand at Woolpert and then in the industry in general, as you see it, I think that'd be really great for some of our students to hear your perspective.
Yeah, absolutely. Thanks, Matt. That's important, definitely. I think you know, with the with the complex world we are living in technology, people looking for, first thing, enthusiastic students, really. You don't have to have the background. I mean, if you're smart and you work hard and you can pick it up, because all of us, Woolpert including, we give enough training. We don't assume somebody out of college gonna know about Lidar, yeah, unless and there is no too many program really teach you Lidar processing or bathymetry processing. That's you're gonna get on the job training. But I would like them to focus on, don't shy away from statistic and understanding accuracy, because a lot of people get intimidated. They think it's too difficult. As a math, it's really simple. It's important for us, two things: datum and coordinate system to be understood very well, and accuracy concept aspects, because people with college, coming from college, they are the best people to bring it to the companies. You don't want to teach high school graduate concept of root mean square and confidence level. That's above their head. But people from college, they need to pay attention to these very high level concept in statistic, which we use, standard deviation, mean, 1 sigma, root mean square, confidence 95, 90, and the datum and coordinate system. Those are, once is understood, then the rest is a procedural, you know, software. They're gonna train you on it to do it, and you will excel if you have these in mind understood, because then you're gonna have put the data you produce with this training under the microscope. Is it good? Is it bad? Is it accurate? And if you don't have these concepts, you get confused. So let them focus on being not shy about tackling this. And I would love to work with them if you have any of them. They want to understand accuracy, how to evaluate a product, geospatial, whether bathy or topobathy, Lidar, whatever, or ortho, how you evaluate the accuracy, how you understand it. And I offer 2 workshops usually at the annual ASPRS conference. One of them really on understanding the new ASPRS, how it is applied to evaluating the quality and accuracy of geospatial product. So, and thus we have it usually in around March time. I mean, I would love to work with them. We can give them either a free pass if you have students, or with reduced to sit in this workshop. They get a good material with it, definitely.
That makes sense. Really great. I think we teach, we do teach statistics at the college here. I think mainly with a fisheries flavor. But you know, those concepts are perfectly transferable, and I wonder if we could talk to our faculty about incorporating some material that's more specific to geospatial.
Absolutely, and let me know. I have a lot of article and publication on it. I can send you. They can use it. They can reference it, whatever they want to. They can use it without any credit. I don't mind. We want people to learn about it. That's all. Yeah.
Yeah. No, that'd be really great. We just started training. I know Kat, who's on the line here. We just did a course a couple of weeks ago that is specific to multi-beam processing.
Okay.
So the students we're going to start churning out from the center over the next 2+ years. You know, they will have some specific background on how to deal with point clouds and geospatial and coordinate reference frames and all that scary math. So I think that'll be a big good benefit.
And let them try to get internship and with Woolpert. I mean, let me know, or if they go to their website and to get opportunity for internship there will be great.
Awesome. Thanks so much.
Sure.
Hey, I actually in CAD, I don't know if I can't see you, but, or maybe you can't see me, either way. But I was just gonna say, thank you so much for the presentation. And as Matt said, I would be very interested in attending the ASPRS. I usually try to, but I also am interested in what you guys were just talking about of like integrating Lidar with multi-beam. And I know that Lidar uses microstation versus multi-beam. We just learned how to use like QPS, and they're very similar softwares. So maybe finding a way to create like a bridge between them would be awesome. And oh, one more thing. I had a question. Someone in the chat wrote earlier about turbidity being a limiting factor, but I was wondering if you've ever thought about like turning it on its head and using LiDAR to measure turbidity instead of just having it as a kind of an annoyance when you're trying to do surveys.
About the measuring the turbidity, you said?
Right, and like looking at attenuation and like turbidity.
Yeah, I think part of the efforts in our lab, they trying to like I mentioned, the Geiger mode, they think it will work better in the turbidity, but that means really you can have a sense of the turbidity or measuring it, you know. I'm not sure how deep they going into that. I can't answer that, but if you want me, I can get you an answer whether anybody doing that.
Yeah, that would be great. I would be interested in talking with them about that.
Just send me an email if you do. They have my email, Sarah. I can share it if.
Yeah, I can get that to her.
Yeah, thank you.
Great. Anybody else have questions? What about Matt? Any more questions for Qassim?
I guess one of your very first slides, you were showing, you said this looks like a DEM, but it's actually, or it looks like orthophotography, but it's actually a DEM colorized with the photography.
Yeah.
I think, was that from a system like you showed later on where you've paired the imagery with the LiDAR, or is that fully constructed from the orthophotography and then colorized itself? How?
Most likely you're referring to one from photography. Let me.
I think it was the query, or looked like a query.
Yeah, no, that's totally from imagery, Matt. That's from
cool.
structure from motion. I produce it actually in Pix4D, if you're familiar with it.
I have heard of it, not used it.
So imagery with a lot of overlap. Yeah. And it gives you ortho and point cloud, and they colorize the point cloud from the.
That's really neat.
It is. It's amazing.
I've seen it done on much smaller scales, like, or folks have actually done like on a little coral reef feature, like, you know, the size of a coffee table, but they, you know, just really cover it, and it's amazing. I don't know how, you know, the research applications I think are, you know, pretty project specific, but you know, being able to do that at scale terrestrially like that is pretty powerful. Yeah. As long you have camera, but the camera have to be georeference, right? I mean, with the LiDAR. Yeah. Either through kind of aerial triangulation, like what we do with the aerial imagery, or if it is underwater and you're not doing kind of photogrammetry, but you need position and orientation of the imagery, X, Y, Z, omega, phi, kappa, things like that. So, but this could be coming from the sensor they're using, whether multi-beam or bathy LiDAR, they all have
GPS and IMU and can be transformed to the camera. The most accurate one when you process the imagery through aerial triangulation to refine these orientation, because the IMU doesn't give you exact, so as the GPS. When you do aerial triangulation, it refines it nicely.
Very cool.
I have one last question, and this may just be my ignorance of how that sector works, but you know, it seems almost like a no-brainer based on what you presented that that this technology would just be standard procedure after, you know, a coastal natural disaster, like, you know, mostly a hurricane, to evaluate the damage and extent of the damage. I mean, is LiDAR moving that way for, you know?
Oh yeah.
Okay.
Oh, absolutely. We've been doing that for the last 20 years.
Okay.
Always after disaster, people hire companies like us to fly imagery and LiDAR. Before we used to only imagery, but now LiDAR, because LiDAR give you volume. That's the nice thing. You can, you know, if you have debris and you want to see a bit what is moved, LiDAR also give you better way of estimating damage on buildings, for example, because you talk about 3D now, not just seeing the damage, but you can measure it in a 3D, yeah.
Great.
I'm just imagining how much different, maybe easier my job. My first job out of school as a marine surveyor in 2002 was modeling longshore transport in Los Angeles County. And we were doing single beam transects with a boat, and then sending a swimmer into the surf zone with a sight glass for theodolite, and then actually doing terrestrial survey on the beach and stitching them all together. And now you could do that, you know, in a couple of days with LiDAR.
With LiDAR,
not be on single beam transects.
Yeah, exactly. And if the project not too long or too big, you can use the drones now, LiDAR on the drones. I mean, the price is going really down now. You can get a good system now from DJI LiDAR with the platform UAS under $20,000. You can use it for precise 3D mapping and imagery. I mean, it has camera too. So you have LiDAR and imagery on the same platform, drones.
Yeah, we have a colleague, Tim Dixon, who's a geodesist and geologist. He's got the drone part of that equation. I might put him in touch with your folks because he is starting to do some shopping for a LiDAR that will go on it.
Yeah.
It'll be a nice little tool.
Yeah, let him talk to me if he wants. I can give him advice.
Absolutely. I had to chuckle when you mentioned, like, you know, we always say the technology, it can't ever get any better, and then we prove ourselves wrong. I ran into one of my old colleagues from 20 years ago at a conference, and oh man, it's probably 3 or 4 years ago now, but we were laughing at how you know, all the sort of, you know, ridiculous wish list things that we had, you know, 20 years ago.
Yeah,
those were obsolete 5 years ago.
Oh yeah.
Wouldn't it be great if we could do this, and this? And
you know,
already blown past that.
Matt, good thing you mentioned it, because before digital world, whether in our business, whether digital camera or LiDAR, if you think about it, the first digital camera, the commercial big metric camera sold, I was in Vienna at the ISPRS, the International Society of Photogrammetry conference, and Leica signed with Japan in 2000, in the year 2000. So that's the first digital camera. And now what, we are in 21, that's what, 21 years? I mean, we saw so many generation like I mentioned, is like smartphone. And those camera expensive, by the way. You talk about million and a half, and in a year time, they come up with something absolutely more than 10 times better productivity than this, and you have to upgrade. But if you look the period that preceded that with the film camera from World War II to the 2000, believe it or not, nothing changed. Nothing changed. The same, I don't know if you're familiar with film. The film camera was 9" by 9" format. The focal length, the lens 6". And we have everything over the year, the same thing. Two company produce it, Zeiss and Veld, Leica now, and that's it. No change in 60, 70 years. But now with the Lidar is amazing. Lidar is just changing every 6 months. Is amazing technology, definitely. You can't keep up with it, yeah.
Yeah, I was born in 1979, which makes me just old enough to have both learned to type on a typewriter and remember looking through at stereo paired imagery the old-fashioned way.
Yeah.
Sarah's like, "What are those?"
Nobody knows what it is. Yeah.
I had a typewriter when I was little, but it was just for fun, though.
My PhD was typed on typewriter. My wife did it actually. She typed it for me.
All right. I think with that, we will say thank you so much for taking time out of your day to join us. This was great. And yeah, we'll get it posted up on our YouTube page, and really appreciate the career advice that you had after Matt's question. That's always really helpful.
Thank you very much. I appreciate that. Thank you for inviting me. And let's stay in touch. Whatever you guys need, I love to help people. Matt, if they need those faculty, if they need to upgrade their curriculum for some courses to insert a little bit more of these statistical, which is directly related to verifying product accuracy, I can send you a bunch of stuff. I mean, for that.
Yeah, I think that would be really appreciated. So we're trying to, integrate more of that ocean mapping twist, at least in a lecture or two, into our standard curriculum. That's more classical oceanography and in the biological, chemical, physical, geological realms. So yeah, that would be great. Appreciate it.
All right.
All right. Thank you. Have a good rest of your afternoon.
Nice meeting with both of you anyway. Have a good
You as well.
Yeah, thanks. Bye.
Thank you.